So now let's try to find a good value between 10 to the power minus 3 and 10 to the power minus 7 for the learning rate. So what we want to do is we want to do something called as cross validation, and this is just a fancy word and we'll talk about it. And what we want to do is we want to do this coarse to fine. So in the first step we want to find like a rough ballpark figure for that hyperparameter. Where does it lie? We know it lies between 10 to the power minus 3 and 10 to the power minus 7, but is it 10 to the power minus 4 or minus 5 or minus 6? So we want to find something rough, and then we want to go search around it and go drill down into finding, okay, is it 3 into 10 to the power minus 4 or is it 9 into 10 to the power minus 5, right? What exactly it is. And this is a tip. So if our loss is any time greater than 3 times the original loss, you would assume, you can assume, it's a rule of thumb, but you can assume that we're kind of going to explode and you can break out. So now what we are doing is we are sampling in the logarithmic space between 10 to the power minus 7 and 10 to the power minus 3, right? So we have 10 to the power minus 7 and we have 10 to the power minus 3, and we are randomly sampling, let's say, a few numbers here, right? And then we are also sampling for our lambda. So we are sampling for our learning rate between 10 to the power minus 7 and 10 to the power minus 3. We are sampling for our lambda 10 to the power minus 5 to 10 to the power plus 5. And then we are running our function train and test loop for 2000 iterations only, because this is the coarse loop, right? So we want to run it for lesser number of iterations. And we are doing this, let's say, in a loop, right? So every time in a loop we are sampling values for learning rate and lambda, and then we are running our train and test loop, and we are then checking for what is the best accuracy we could get with those hyperparameters. So we have run it many times, and we see that there are some models, some choice of these hyperparameters, some values of the knobs that we have turned that give us some decent accuracy numbers. So here we see that, okay, for let's say lambda of about 0.1 and learning rate of about this 10 to the power minus 5, we are getting like a good validation accuracy of about 34. Right? Remember, we're only doing 2000 iterations. Also remember, it's a very tiny linear network, right? It's a linear model, right? It's just a matrix vector multiplication. So we should not expect too much out of it, but at least from here we got validation accuracy of 34 here, and we got a 31 here and 27 here. So then what we want to do is we want to kind of drill down there a little bit more, right? So wherever we got like 37, so we got so we will now adjust our range. We were sampling in the range of this and this, and we want to adjust it to something which was working better in our coarse search. So our coarse search, we found some numbers which were doing well, and now we'll do a finer finer search around those numbers. But remember, we have to be careful to find to know that when you are doing the finer search, this coarser were not lying at the boundary of where we were searching, right? So just be careful of that. And we then, through our coarser search, found that we're getting like a 37% accuracy for this one layer neural network and only 2000 iterations, right? And we're getting this 37 with a learning rate of about 10 to the power minus 4 or 5, along with, let's say, a lambda of about 2. So we will remember this, and then we will, and like I said, we'll make sure that the best ones are not at the boundary of what we are sampling. If it's at the boundary of what we are sampling, we should be careful. We should relax the boundary and sample a bit more. So this is, so we have kind of found like a good hyperparameter here, and this is how you do that hyperparameter search. And once we found good hyperparameters, you would want to train it for a longer period of time. One good thing to know is, so there's this paper by Brekstra and Bengio from a long time ago, from 2012 at NeurIPS, at JMLR, and what they claim is you should not do that grid search. You should not search. What does it mean, grid search? Let's say this is your lambda and this is your learning rate LR on this axis, right? So this is your learning rate, this is your lambda. And what we kind of found is that your learning rate is more sensitive, lambda is more robust. So lambda is, let's say, a less important hyperparameter. And now if we do random search, we only search for, let's say, so if we do grid search, so if we do this grid search like here, we only sample, let's say, 10 to the power minus 7, 10 to the power minus 5 and 10 to the power minus 3. And let's say here it's 1, 10 and 100. But when we do random, then we do more sampling. So here what he means to say is, when you sample, so here we could only kind of come up with these points for the search, but when we do these random searches, we get a better distribution, we get a better sampling. So random sampling is better. I recommend you kind of briefly read this paper, but the message is very simple. The message is, don't do grid search, just do random searches across your hyperparameters. And this is because there are some hyperparameters which are less important and some which are more. Now another thing that you can try is MLflow, that helps you keep track of the various hyperparameters that you have tried. So for example, here you see that there is the hyperparameter so-called momentum. We'll talk about it when we talk about loss functions. There is also, let's say, learning rate, and this is the final loss, right? And loss lower is better. So we see that there are some hyperparameter combination, let's say this which leads to high loss. Also all these hyperparameters are bad because they all lead to high loss, but then there are these hyperparameters, the blue ones, which are better. And then we want to kind of drill down into which hyperparameter, maybe this one and this one is probably that gets the best, or maybe it's, let's say, this one and this one that kind of gets us the best training loss or test loss, or whatever metric is that we're looking at. So this is one good way to kind of keep track of all your experiments, which is MLflow. Now this is that course to find that I was talking about. So once you've done your course selection, then you want to run for this longer time on. So once you have kind of narrowed down, okay, maybe this is a good hyperparameter that I want to use, then you want to run those experiments for a long time. And this is Karpathy's cross validation command center, and experiments like these, right, or these where he knows that, okay, it's not going well, he would kill quicker. And then experiments which are going good, he would then train it for longer time. And now you can use weights and biases, you can use tensor board. You don't really need to kind of build this yourself. This was long time ago, before these good things existed. This is my own command center long time ago, and it is interesting to see all that we are seeing here. So we'll take 2 minutes to look at it. So this was for human pose estimation, meaning we want to find 2D joint locations for body joints, right? So suppose you have your human, such as this, right? And this is, let's say, the shoulder, and let's say this is the elbow, okay? And what we want to find are joint locations, right? So x comma y for those joint locations in images. Here we have two models, right? So we have and you cannot read, but the green one is the validation loss of model 1, right? So let me call it model 1. The red one is the training loss, right? So training loss of model M1. Similarly, this is the validation loss of model M2, and this is the training loss of model M2. Now look what is happening here, right? So training loss is less than validation loss, and this makes sense because you are actually optimizing your parameters based on the gradients that you get from the training set, right? Because based on the training set you got the output, and through the output and the target you got the loss, and then you back propagated it and changed the weights. So your training loss should always be less than your validation loss, and this is what we see both for model M1 and M2, right? Because M1, the training loss is your red one, and for model M2 your training loss is that blue or purple one. For your model M1, your validation loss is that green one, and for model M2 your validation loss is that cyan one. Now what we want to also understand is which model is better, just based on this curve. obviously model M2. And if you look at this, at least my example closely, you will see the difference between M1 and M2, right? So this is M1 and this is M2. And if you look at the diff, you will see that there are more number of parameters in M2 versus M1. So we'll talk about again convolutions in this week, but here you will see that we have way more convolutional features in the second one here as compared to the first one. Here we have these 16s and here we have these 128s. So it's a bigger model. And on the x-axis we have number of iterations or epochs, and on the y-axis is of course the loss value. And you see that the bigger model, I have only run it for lesser number of epochs because we didn't have so much time, right? But the smaller model, I ran it for larger because I may have left it to run overnight, and I came back in the morning and I saw that it has kind of done maybe my full 300 epochs that I had initially set up with. So now that is something, so here you see the big model is false and here the big model is true. So I had wired up my code such that whenever the big model is true, I have more number of features, the feature maps. Here, these are my accuracy curves, right? So you see my accuracy curve for the face, for the shoulder, for the elbow, for the wrist. You see that the accuracy curves are usually very high for the face and the shoulder, but they're not as high for, so you see it only gets to, let's say, wrist, it's only getting to, let's say, 60. And what is x-axis? It's basically pixels, and what is y-axis? It's a percentage. And what this curve means in this case is, let's say at 10 pixels, I'm getting about 75% of my data set correct, right? So it is basically, so this is error is called the PCK metric, and what it says is, okay, within, if I draw a ball of say 10 pixels around my true face joint, what percentage of my data set did I find in that ball, right? So here, if I go further, then a ball of, let's say, 40 pixels, I get about 90% of my data set. If I look at my, let's say, elbow joint here, so this is, remember, is my elbow joint, I see, and again, red and green are again test and training, right? So this is, the higher one is always training and the lower one is always test, because training is something that the model looked at, right? Test is something that the model did not get to look at. So training, it should always be less. So here you see with a 10 pixel ball, I'm getting maybe about, how much is this? About, let's say, 55% of my data set correct. But let's say with 45 pixel ball, I'm getting about 75% of my data set. And it is very important to look at all this while training your model, right? Your losses, your training loss, and so here we looked at our training loss and validation loss. Compare between different models. Here we are looking at our metrics, right? So this is not directly differentiable, this is not your loss, but this is the final metric that we are interested in. This is over epoch, right? So this kind of shows that, okay, by the time we are at, let's say, epoch 15, we are almost done. If your data set size is too big, you would do it at the iteration level instead of epoch level. Now, this is also very important, right? This is the qualitative visualization. I want to actually see what my errors look like. So you will see that for faces, it's finding the face at the wrong person. Similarly, also with the shoulder and elbow, right? So we are given like the torso location and we need to find the right person, but somehow I find the wrong person. But let's say with my wrist, some weird things are happening, right? So this is the ground truth, but it is finding wrists at, say, at the foot or other places. It's finding somewhere at the outside the image. And this is all back from about 2013, just about when AlexNet came out. So it was very primitive. We were the first person to do heat map based human pose estimation. Heat maps are more robust to multimodality because, your hands might look the same, but you have to be able to deal with this multimodality. We'll talk about this maybe in a live session, but the message here is that you have to look at all those quantitative things, and along with those quantitative things, you also have to visualize if you have the capability to, or listen to it in your ear if it's speech, or read the text and see what is happening. But you have to kind of analyze all of that, because as humans, we are able to see patterns and then we are able to make some, qualitative intuitions about what is going on and how we can improve our model. So I cannot stress it enough, but if you take anything from this session, from this video, remember you have to look at your data a lot. Right? I spend maybe an hour or two just looking at my data, just to get a feel for what my data looks like. And I visualize those screens where I look at, if you're looking at images, I look at, let's say, 20 by 20 images. So in one screen, I will have, say, 400 images in this 20 cross 20 grid. And I'll look at all of those 400 with their labels. And we, as humans, we are able to look at those 400 fairly quickly. And I will sample from my data set, and I will look at all such, a lot of these 20 cross 20 grids. So that's on the data set kind of things. Then we saw about like the hyperparameter, the model, but then the final analysis side of things, right? So we will look at a lot of, let's say, quantitative metrics, but then also qualitative. What actually came out? What was my actual result on my data, right? What is the model saying? So look at all of that, and that is what will get you to the model that you're, wanting to train. Now these are good things to know. So for example, this is what you would expect your loss curve to look like, right? It'll be a little bit jittery, but so this is over iteration. So this here you can have epoch. What is it? What is an epoch? An epoch, we say we have done one epoch when we have looked over our entire training set, right? So that is one epoch. Next, when we then the second epoch, we are again iterating through our entire training set. So those are epochs, and every batch is an iteration. Right? And another thing I forgot to mention when we were doing backprop is when we do backprop and when we have batches, we average the gradients. And this you would have seen in your last week's assignment already, but it's again good to know. Now, usually when you have, your loss exploding, it means your learning rate is too high. If your loss is not going down right, you would say your learning rate is maybe a bit low. This can, a curve like this where it flattens very quickly can also be a candidate for, let's say, a little bit high learning rate. And a good learning rate, you should have this consistent going down of your loss curve, of your training loss curve. Now, there are also these learning rate schedules, right? And we have to be very careful about this learning rate decays and these learning rate schedules, but it helps. And when we talk about optimization, we'll talk about it, right? So the learning rate basically divides the step that we take in the negative direction of the gradient. Is it like this much or this much, right? So what is the size of my step that I will take in the direction of the negative gradient? Now, if it is too big, you go in the negative direction quickly, but then what happens is, like suppose this is where I need to get to, this is my local minima, and let's say I started from here. Now, if my learning rate is too big, maybe I came here first, and then from there, because my size will always be this much, right? So then I will go here and I will just keep bouncing around here, right? I will never get very close to my actual place that I want to get to. If my learning rate size is too small, I will maybe go too slowly, right? Maybe I'll not get there because it's not as smooth as this, right? My loss curve looks a little bit like this. So, but then if it is the right size, what will happen is I will take a step, I will take a step, I will take a step, and I will get to the right part, right? Even if I take a step from here, I'll maybe here and here. So I'll bounce around and I will be in the regime of the right part in the loss function. But what is this learning rate decay? What it is doing is, so I'll draw it here. So what it is doing is, let's say our learning rate was the right size. We are kind of getting here, and then we are getting here, and then we are getting here. So we are bouncing around this, right? So when you are bouncing around this, we want our learning rate to become smaller so that we can get to closer to the local minima. So if we now start taking smaller steps, we will eventually get to our local minima, and that is what it means by reducing the learning rate. But we should be very careful about when to reduce the learning rate. Do not reduce the learning rate early on, because that will just basically mean that we are not able to get to the local minima. It is only after we are bouncing around that local minima we should reduce the learning rate. So be very, very careful about reducing the learning rate. I would say don't reduce the learning rate only when you're 100% sure that your loss has plateaued. It means that you're bouncing around the local minima. Only then you should. What happens is, suppose this is our loss curve. So let me draw it on the next slide. So forget about this, we'll talk about it. But what I want to say is, suppose this is what your loss curve should look like, right? So now only when you're sure that you have plateaued, you should hit the learning rate multiplier. And when you hit, let's say, a constant learning rate multiplier, it would look like this, because now it will reduce a little bit. And something I want to show you is that you will see this in my loss function if you look very closely. So you see here, or you see here, this is when the learning rate multiplier was hit at maybe epoch number 50. Right. So this is also here, you see the learning, initially it's a little bit, let's say, noisy, but then after hitting the learning rate multiplier, it becomes more smooth because the step size becomes smaller. But you have to make sure that you don't hit it too early. Otherwise, let's say we hit it here, right? So it will maybe do this much, and then it will eventually lead us to an inferior model. So be very careful about hitting your learning rate multiplier is the message. Now you might see a loss like this one. So this can happen. There is a phenomena called as grokking. There is also a phenomena called as double descent, right? So these are very interesting phenomena. And it happens mostly with these large models, but in this case, if it's a small model, it may be let's say candidate for improper weight initialization, right? So bad initialization could be a suspect. But these two things that I have mentioned, we'll talk about it in small talk. Maybe we'll touch upon it a little bit in one of our live sessions, or talk to about this with your TA. But these are interesting phenomena because of which your loss curve can look like this one. Now this is again very important, right? So this is your this is your metric, your validation set, and this is your final accuracy or whatever metric, right? So we are calling it accuracy here, and this is your training set accuracy, this is your validation set accuracy. You see here, this is your training set accuracy, this is your validation set accuracy. Now your training set accuracy will always be higher than validation set accuracy, but if the gap is too big, it might mean that we are overfitting, right? It means that we are doing very well on our training set, but we are not doing well enough on our validation set. So in that case, what you may want to do is you may want to increase your regularization strength. You might want to make your data more difficult by doing these so-called augmentations, which we haven't spoken about, but we can talk about it later. You might want to reduce your model size. You may want to increase your regularization. So do anything, but do something so that you prevent this overfitting. If there is no gap, right? If, for example, your training and validation were almost the same, it would mean that you have to so you're underfitting, and you might want to increase your model capacity. You might want to reduce your regularization. You may want to reduce the augmentations that you're doing to your data, right? So this is again things that you should think about when you're training models. This is another neat thing that you can try, but this comes like when you're going deep down the rabbit hole, when things are still not working. What you want to check is the scale of your magnitude. So the weight update that you're making, right? So we are doing W dash is, let's say, equal to W minus lambda times your derivative of loss with respect to your weights, right? So this full quantity that we are doing and the magnitude of this, right? So you can just look at the magnitude of this. This should be about, let's say, 0.01 or 0.001, right? So it should be about 100 to 1000 times lesser than the full magnitude of the weights. And for our case, for the model that we were training, our linear classifier, it happens to be, let's say, about 0.1. But we are saying it should be about, let's say, 0.001. So it should be 1000 times lesser, because you should be able to at least do 1000 updates before you change the weights, kind of a thing, right? So this is again something that you can do. You can monitor how much is the update you are doing to the weight. And then these are like a lot of other additional things that you can look at. I'll briefly go through it because it's not very important for what we want to do. But if you were to visualize your activations, they should look sparse. They should not have this kind of, let's say, patterns, right? It may base, also it means that, you know, there are some activations. So these are outputs of individual neurons, and these neurons are always off. That is a bad sign. And here it's good because hidden units are sparse across samples and across features. So these are different samples and these are different neurons. These are for convolutional layers. Again, we don't do this anymore because we usually use these pre-trained convolutional filters. But if you visualize them, you will see that, you know, your convolutional filters, especially the initial layer convolutional filters, look like these. And we call them as Gabor filters or edge detectors. And we'll talk about this when we talk about convolutional layers. Again, this is very interesting, but I will create this as, let's say, a puzzle, right? So the puzzle is that, you know, we are training, let's say, a MNIST classifier, and this is the fully connected layer, and this is the fully connected. It's a single layer, right? So it's again like a single layer model that we have trained, and the input is 784 because it's 28 cross 28. So 28 cross 28 is 784. And the output, so this is not the single, so this is not a single network, a single layer. There are multiple layers here, but the first layer takes my 784 to, let's say, 300, right? And when we look at this, it has this band structure, and the question is why? Why do our weights here have this band structure? Why is there no weights learned here, and why are these weights around 0, right? So white means around 0 and blue means higher than 0, and remember it starts around 0. So why did some weights not learn at all? Yeah, so think about this. It's a question, and I want us to be able to answer this question in either our, you know, platform circle or in one of our live sessions along with your TA, but this is something that we need answers to. Yeah, and then these are again things that we will post. This is just a recap of all that we have spoken about, and these are just good things to know. There are also a lot of tweets, there are packages. We will post about all this below the video today, but remember that we have to think about all this, and the most important thing, and this and this and this, you know. So yeah, I mean, but the only thing, if you were to take anything from this session, is look at everything closely, specifically data at the input and at your test and validation, right? Look at visualize them, look at their labels. Also at output, visualize them, look at the labels. Of course, you will also look at all the quantitative outputs, the loss curves, the metrics, the accuracy numbers and everything, but there is a systematic way to do it. Start with, you know, a small network, start with something simple, start with those smaller data sets, smaller batches, turn off regularization, turn off data augmentation, look at all this systematically, and we will, as you know, this is a very hands-on practical course, so we will actually go on training networks and you will get practical experience of doing this, but remember to use these techniques in your future endeavors.